We are giving a quick crash course on trigonometry today, starting with degrees and radians, right? Degrees are the standard measure of angles, and radians are an alternate measure, which, it's useful in higher level math, but it's something that we do learn in trigonometry. And the main thing we need to know about degrees to radians is a quick just conversion from one to the other, because there are sometimes you want to be able to convert from degrees to radians, which is nice when you're working with angles, right? Degrees are kind of where most of our knowledge lies. And it's also imperative to be able to use radians, because sometimes our answer has to be given in radians. So we do want to know how to convert from degrees to radians, and also from radians to degrees. If an angle is given to you in radians, you can always convert it to degrees, again, because that's where most of our knowledge lies. We can use that to draw our angles and things like that, right? So in order to convert from degrees to radians, we're going to take our degree measure, multiply it by this ratio, pi over 180. Here is an example. Let's take something like, let's say 60 degrees. Right, we're going to multiply this by pi over 180. And that will turn this size a little bit better. Pi over 180, right? We can cross cancel here, because we can divide, basically we can reduce by a factor of 60, and this is going to equal 1 times pi, which is pi, and 1 times 3, which is 3. So pi over 3 is the equivalent radian measure. Radians will need to be given in terms of pi, right? Radians cannot, in my class, be given as a decimal form unless it's really, really explicitly noted. But this is going to be sufficient for a degree measure. So that's an example of converting degrees to radians. What about radians to degrees? Let's say you have an example of a problem which is asking you to, I don't know, let's say it wants you to draw an angle that measures 5 pi over 4 radians, right? Once again, it's tough to know what angle this actually is, so let's multiply by this ratio. Pi 180 over pi is going to help us convert this into degree measure. And once again, we can cross cancel here. 180 we can over 4, we can divide by 4 on top and bottom to get 45 degrees, or 45 on top and 1 on bottom. And something else that can be cross canceled here is the pi terms, right? So the pi terms are going to be gone, and all we have left here is 5 times 45, which is equal to 225, and that is, again, once again, a degree measure. So now we know that we can draw a 225 degree angle. The unit circle is something that is very prevalent in trigonometry. And what the unit circle basically states is that a circle of radius 1, right? And this is, very blown up, because if the radius is 1, this is a tiny circle on an xy axis, because this circle again is sitting on an xy axis. Right, what we can see here is, let's actually take a look real quick about what we're really looking at, right? We're looking at an xy axis. I will draw a quick xy axis right here. Let's center this right on a grid line. And what we are looking at here is a circle that is that big, right? 1 unit in radius length, right? And excuse me. Well, 4 of the major points here are these 4 points right here, right? So what we're looking at, excuse me. What we're looking at is this circle here, just blown up a whole lot right here, all right? The radius is equal to 1, and we have these 4 points here. That is 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And what these points here represent is actually if this is a unit circle, again, this is unit circle because the radius is equal to 1 and it's centered at the origin, that means every ordered pair here that is an x comma y, and remember in pre-calculus we kind of talk about this as an x, f of x, input, output kind of deal, input, output. Well, the unit circle actually gives us another representation of this ordered pair, and that would be the cosine of theta and the sine of theta. In trigonometry, we draw angles like so. Starting here at the positive x-axis, and another length kind of swinging up, and it doesn't have to be that long. I mean, it can be, as you know, the length of this line here can be whatever. It can be as long as it wants, but over here there is a point of intersection with the unit circle, and this point of intersection happens at an x comma y ordered pair, which can be represented by the cosine of an angle theta and the sine of an angle theta. And where is this angle theta located? The angle theta is located, I will show you once I delete that. The angle theta is actually located right here. So if we are able to determine what this ordered pair is, that means if we draw an angle starting at the positive x-axis and swinging over to intersect that point, if we know what that x comma y coordinate is, we can use that to determine the sine and cosine values. Right, so what if this angle, let's delete this for a minute. Let us delete this for a minute. What if this angle actually stopped right there? Right? What if theta was equal to 90 degrees? How would we determine the sine and cosine values? Well, this line intersects the unit circle at this ordered pair 0, 1, which tells us that the cosine of 90 degrees is equal to 0, and then the sine of 90 degrees is equal to 1. And it can be that simple as long as we know all of these things about the unit circle, as long as we know what these ordered pairs are. And that's really what the unit circle tells us. At what's called a quadrantal angle, that would be 0, 90, 180, and 270. Right, there are angles that we can know the exact value of those sine and cosine terms. So when we draw an angle in trigonometry, we are always drawing this first. This is called the initial side. And it is always located right there, always located on the positive x-axis. The other side is called the terminal side, and that's the one that kind of swings around. You know, it can stop right there and measure 90 degrees. It can stop right here and measure 180 degrees. It can stop right down here and measure 270 degrees. Right, it can do all those things. It can even stop right there. It can go around here and stop right there like that. Right? This terminal side, and it can intersect the unit circle right there. This terminal side can swing around and around in any direction and stop wherever it wants to. All right? There's two things about this. One is the quadrantal angles can be measured based on their ordered pairs of where they intersect the unit circle. Right? That's something that we just saw. All right, let's try another one right here. This is an ordered pair of -0, comma -1. Right, that's this ordered pair right here. So we wanted to find the cosine of 270 degrees. We could look at this number and it's 0. If we wanted to find the sine of 270 degrees, we could look at this number and it's equal to -1. Again, these quadrantal angles here, 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 and here are that simple. Take a look at this though. I wrote down two measures here. One of them is 0, the other one is 360. So let's say that the terminal side didn't move at all. That would be a 0-degree angle. Right, I'll draw that in, let's say, purple. Right, here is a 0-degree angle. Now let's look at this light green color. Let's say it went around all the way and stopped after one full revolution. That would be a 360-degree angle. But if you notice, the purple and the green angles I made end up in the same spot, right? It's possible because, again, there's only a full circle here for this thing to this terminal side to move around. You're inevitably going to have some duplicates. So something like 360 degrees and 0 degrees, they do have cosine and sine values. The cosine of 0, again, this ordered pair is 1, 0. So the cosine of 0 is equal to 1. The cosine of 360 is also equal to 1 because the terminal side ends up in the same location. This phenomenon, this pair, they are called coterminal angles. Truth be told, this terminal side can swing however many times it wants to. 720, 1080 degrees. The cosine and sine values at all of those angles, as long as they are coterminal, they don't have to be 360 degrees apart. They have to be some multiple of 360 degrees apart. Maybe 360, maybe 720, or something like that. Those sine and cosine values are going to be the same. They are going to be exactly the same. I will illustrate this once again. Let's take a look. Again, on top of an XY axis. Let's take a look. I will draw an angle here. This is the initial side. And let's say the terminal side goes here. Right? Let's suppose that this angle, we'll call it theta. Let's say it's equal to 100 degrees. 90's up here, 180's over here, which means that 100 is going to be somewhere here in what is called the second quadrant. And let's say that there's another angle that goes around like this and stops right there. And I'll make this in green. All right, what is the measure of this angle? Let's say this angle measures 460 degrees. Right, we'll call this theta 2, and the first one will be theta 1. So theta 2, I'm telling you, is equal to 460 degrees. So what is the difference between these two angles, theta 1 and theta 2? 460 minus 100 is equal to 360 degrees. These are coterminal angles. So whatever ends up being the sine of 100 degrees is going to be exactly the same as the sine of 460. And that's something we will come back to. But it's something that you do have to know. This is called coterminal. And angles can be measured positive or they can be measured negative, right? I told you about these angles here, and if you looked at the way I drew, or I'm drawing a little arrow here, these angles are going in a counterclockwise direction. And that means that the angles are measured in a positive manner. Angles can be measured in a clockwise direction. And that means that the terminal side is going to swing in a clockwise direction. And that means theta here can be something like, let's say, negative 50 degrees. right? Because the angle has a negative degree measure or a negative radian measure. That means the terminal side went the other way in a clockwise direction. Let's say that there was a negative angle. Let's call this theta 3. Let's say theta 3 is equal to negative 260 degrees. Right, how do we know where that ends up? How do we know? Because, drawing a negative angle might be a little bit difficult, right? Negative 260 plus 360 degrees is equal to, look at where we are, 100 degrees, another coterminal angle, right? So angles can be measured either positive or they can be measured negative. They will mostly be measured positive, but negative does exist. And you can always put them back into any angle, whether it's very large or whether it's less than 0. You can always put it back into something between 0 and 360 degrees. Right? And you do that by adding or subtracting 360 degrees to either bring that angle up or move that number down. Okay? There are 4 quadrants on an XY axis. X and Y. And trigonometry makes use of all of them. In quadrant 1, every single trig function, that's sine, cosine, tangent, and their counterparts, cosecant, secant, and cotangent, all 6 of these trig functions are positive in the first quadrant. In the second quadrant, quadrant number 2, the sine function is positive along with cosecant. Right? The 3 main trig functions in trigonometry are sine, cosine, and tangent. Cosecant, secant, cotangent are the extras. But S means that quadrant 2, sine function's positive, everything else is negative. Right? Sine and cosecant are positive, everything else is negative. T in the third quadrant stands for tangent and cotangent. These are positive in the third quadrant. Everything else, all 4 of the others, are negative. And quadrant 4 is where cosine and secant are positive. Right, so a nice mnemonic for this is all students take calculus. Right, starting from the upper right-hand corner, traveling in a counterclockwise direction, ASTC is a little mnemonic, a little helpful tool so we can remember which functions are positive and which functions are negative. Another thing we have to know about trigonometry is the special right triangles, right? Every right triangle can utilize a squared plus b squared equals c squared, the Pythagorean theorem. But there are 2 special right triangles, and what makes them special is their angle measures. Every right triangle has a 90-degree angle, but there's a special right triangle that uses the 3 measures of 90, 30, and 60 degrees. And this is a 30, 60, 90 right triangle, which has special measures of 1 across from the 30-degree angle, 2 across from the 90-degree angle, and radical 3 across from the 60-degree angle. Right, so as long as you draw a 30, 60, 90 right triangle, that means you can fill in these 3 side lengths always, right? In a general sense, these are proportional because they're similar. Every 30, 60, 90 right triangle is similar, right? So if the opposite 30-degree measures, let's say, x, that means the hypotenuse here is going to measure double that, 2 times x, right? And again, that's something that's viewable based on the short side, which is what I call the bottom here. I call it the short side. The short side measures 1, and the hypotenuse measures 2. So if the short side measures 10, the hypotenuse is going to measure 20. And over here, x times radical 3. All right, so this is a proportion you can always fill in, but for our trig purposes, we're going to be filling these in with these measures here, 1 and 2 and radical 3. Take a note with the 30, 60, 90 right triangle. If the 60-degree and 30-degree measures flip, like they did here, notice that 30 is on top and moves to the bottom. the 1 and radical 3 sides are going to move accordingly. They do have to move with the angles. The side that measures 1 is always opposite the angle that measures 30. It is always opposite, right? You can take your finger and slide it over to the other side of the triangle, and there is your side that measures 1, okay? The other special right triangle is a 45, 45, 90 right triangle. Oh, back to this, sorry. So in the same manner that this 30 degree is opposite 1, the 60 degree is opposite the radical 3, okay? So those have to move accordingly. Those have to be paired up that way. A 45, 45, 90 right triangle has side measures of 1 and radical 2 for the hypotenuse. And this is slightly easier because since these angles here are the same 45 degrees, that means opposite those angles is going to be the same. They're each going to measure 1. So last thing I want to talk about here is what's called a reference angle. A reference angle is a positive acute angle, and it represents an angle of another measure, right? And we'll see how that's useful when we do some examples. The important thing about a reference angle is that it is always made with the terminal side of your angle and the x-axis. Always, always, always the x-axis. You never ever make a reference angle using the y-axis. And the reference angle is going to look different based on each quadrant, right? If I look at this picture, this diagram is pretty good. Take a look at where in red this reference angle is located. Again, always against the x-axis. And in each quadrant, you're going to have a reference angle. And in each quadrant, you're going to be able to find a reference angle by doing something different. If your terminal side falls in the first quadrant, then your reference angle is the same as your angle measure. If your terminal side falls in the second quadrant, then 180 minus your angle measure gets you the size of this reference angle. In the third quadrant, you can flip that around because this terminal side, this angle measure is larger than 180 degrees. Take your theta minus 180 and you can find your reference angle. And then your reference angle is located right over here in the fourth quadrant. 360 minus that theta, which is your given angle, that's going to get you the measure of this reference angle. Right, so you can look at this chart here, which shows you all four at once. And over here, you're seeing reference angles in each separate quadrant. Notice that the theta is given in blue and the reference angle is given in red. So let's take a look at the third quadrant. Let's zoom in over there. Right, we have theta here and the terminal side right there, and the reference angle is located right there against, again, the terminal side with the x-axis. So let's use all of these pieces here to find what's called the exact value of the sine of 2 pi over 3 radians. Now the first thing we want to do here is take this 2 pi over 3 radians and convert it into degrees. Why? Because, again, degrees is where most of our knowledge is located. So again, let's take 180 over pi as our conversion rate. Cross out the pi's because they cancel out. 30, that's a 3. We can divide by 3. 3 divided by 3 is 1. 180 divided by 3 is equal to 60. And now we can multiply 2 times 60 to equal 120. So a couple things here. The sine of 2 pi over 3 radians is equivalent to the sine of 120 degrees. They are the same, it's just two different angle measures. Not different, actually, two representations of the same angle measure. So what we're going to do now is draw ourselves our 120 degree angle. Again, we always start here on the positive x-axis, and this angle in particular is going to swing here, and it's going to stop somewhere there. You don't have to be exact. We don't need a protractor or anything like that, but this angle is 120 degrees, so it does sit somewhere between 90 and 180. And now what we can do is identify this as an angle in the second quadrant, quadrant number 2. We can draw ourselves our reference angle. We can identify our reference angle, and we can also use our chart here to figure out what the reference angle is going to be. Right, the reference angle, we want to get just this piece right here. So if we take 180 minus 120, right, because 180 would be all the way out here, and 120 is over here, so we're just looking for that piece in between. This is equal to 60 degrees, and this is our reference angle measure, 60 degrees. So here's how we're going to use our 60 degree reference angle. I'm going to draw another diagram focused in on the quadrant number 2, because that's where all of our action is going to be right now. So here is our quadrant 2 kind of zoomed in, and our angle here measures 60 degrees because we calculated that right there. And what we're going to do now is draw what's called a reference triangle. The reference triangle must include your reference angle, which means that this reference triangle must be made with the x-axis, because that's where the reference angle is made, with the x-axis. So what have I drawn here? I have drawn a right angle. This is your reference triangle is always a right triangle, because this is what we drew in. So I made this angle 90 degrees. We knew this was 60 from our calculations. That makes this angle up here 30 degrees. This is a 30, 60, 90 right triangle. And remember what we said about a 30, 60, 90 right triangle? We can fill in our side measures. Opposite the 30 degree angle, we can fill in a side measure of 1. The hypotenuse, we can fill in a side measure of 2. And the side opposite 60, we can fill in a measure of radical 3. Here's where a reference angle comes into play. We calculated the sine of 2 pi over 3 is equivalent to the sine of 120. Now what we're doing is calculating the sine of 120, but we are using our reference angle in place. That's when I said before, is that a reference angle is a representation of another angle. We are using 60 degrees to represent 120 degrees. We are using the sine of 60 to represent the sine of 120, right? So this here, 2 pi over 3 and 120, is a direct substitute without anything else to be aware of. But when you substitute this 120 for 60, this is something you need to be aware of. Is this going to be positive or negative? Because it's possible that our replacement can create a negative, right? Remember that in quadrant number 2, the sine function is positive. So how are we going to figure out what the sine of 60 is actually equal to? Based on something that I did not mention today, but you should be aware of, SOHCAHTOA is a little mnemonic that helps us remember that sine is equal to opposite over hypotenuse, right? From our reference angle, this is the opposite side. And in our right triangle, this is the hypotenuse. So that means that the sine of 60 is equal to radical 3 over 2. And again, we have to be aware that this also could be a negative radical 3 over 2, depending on the trig function we are trying to calculate and the quadrant that this angle is in. Since this is a sine function in the second quadrant, that means that positive radical 3 over 2 is our correct answer, not the negative. Excuse me. Let's do another one. I will do this one a little bit faster. This is trying to calculate the cosine of 1410 degrees. So because this is a very large angle, the first thing we're going to do here is Subtract 360. 1410 minus 360 is equal to 1050. 1050 minus 360 is equal to 690. How do I know when to stop? 690 minus 360 is equal to 330 degrees, and here is where I will stop. Why? Because we want our angle to be between 0 and 360. Stop when your angle is between 0 and 360 degrees. All right, so since we got 330, now I know to stop. This is where coterminal angles come into play. When you are given an angle that is above 360, or if you are given an angle that is less than 0, you can always either subtract 360 in our case, or if it's less than 0, you can add 360 until you find a coterminal angle that's between 0 and 360. So if we draw an angle here, starting at the initial side, and go 360, 720, 1080, and then just even more over to 1410, and we have the angle like that in red. Now in green, I'm going to draw a separate angle. It's going to start at the initial side like it always does, and this angle is only going to travel 330 degrees. Now watch how this angle travels. It stops at the exact same place as the 1410. The cosine of 1,410 degrees is 100% equivalent to the cosine of 330 degrees. So we don't even need to draw our 1410 degree angle. We can draw a 330 degree angle, and then we can be on our merry way. We can continue with our diagram, right? We can continue with our diagram and drawing our 330 degree angle and going from there like we should, right? This is the initial side. This angle swings around past 90, past 180, past 270, and stops somewhere before 330 degrees. Sorry, before 360 degrees, right? This is a 330 degree angle, and this creates a reference angle right in that blue location right here. What is the measure of this reference angle? 360 minus 330, because we are in quadrant number 4. That means we're going to do 360 minus theta. This angle measures 30 degrees. So let's draw a new diagram. Let's start fresh so that we can zoom in and we don't messy up. Again, so we have here, this is our terminal side. Our reference angle measures 30 degrees that we calculated. And the next step here is to draw our reference triangle using the x-axis. That's 90 degrees. That makes this 60 degrees. So again, we're finding the cosine of 1,410 degrees. Through the use of coterminal angles, now we are finding the cosine of 330 degrees. Through the use of reference angles, we are finding the cosine of 30 degrees. And since this is in the 4th quadrant, this cosine of 30 is either positive or negative. In the 4th quadrant, the cosine function is positive, right? If this was any other trig function, sine or tangent, it would be negative. So what's the cosine of 30 equal to? Remember, this 30, 60, 90 right triangle has side measures of opposite 30 is 1, opposite 60 is radical 3, and then the hypotenuse measures 2. And with SOHCAHTOA, we are looking at cosine is equal to adjacent over hypotenuse. Adjacent is up here next to our reference angle. Hypotenuse is opposite the 90-degree angle. So we're looking at this equaling radical 3 over 2. And again, the answer here is positive. I should have switched it up so you can see a negative answer. But it's fine. That's fine. So let's do one more, which in this case is both negative and in radians. The first thing we want to do is convert this into degrees. Very first thing, if your angle is given in radians, negative 3 pi over 4, let's multiply by 180 over pi to get it out of radians mode. Pi's cancel out. We can reduce by 4. So we get 45 on top and 1 on bottom. Negative 3 times 45 is equal to negative 135 degrees. Now, since this is outside of our range, where theta should be between 0 and 360, let's take negative 135, and this time we're going to add 360 degrees to it to see what comes up. Negative 135 plus 360 is equal to 225 degrees. So again, we're looking at the tangent of negative 3 pi over 4, which means we're looking at the tangent of negative 135 degrees. That's through a radians to degrees conversion. Now, through the use of coterminal angles, we are looking at the tangent of 225 degrees. Let's draw our 225 degree angle. All right, this thing is going to end up in the third quadrant. 90 over here, 180 over here, 270 over here. So since 225 is somewhere in between, initial side here, terminal side swings around, ends up right there. This is a 225 degree angle, and our reference angle is located in between the terminal side and the x-axis like it always is. So 225 minus 180 is equal to 45 degrees. This is our reference angle. So once again here, we're looking at the tangent of 225, but instead either positive or negative tangent of 45 degrees. This is the third quadrant. So once again, this is going to end up positive because tangent is positive in the third quadrant. I'm realizing all three examples are positive, and again, I do not want you to think it always works out that way. So let's draw our reference triangle using this 45 degree angle. 45, 45, 90 right triangle now. Remember, on a 45, 45, 90 right triangle, it had a hypotenuse of radical 2, and it had legs equal to 1. SOHCAHTOA, tangent is equal to opposite over adjacent. Opposite is over here, that's 1. Adjacent over here is also 1. So that means the sine of, no, not the sine, I'm sorry, tangent of 45 is equal to 1 over 1, which is equal to 1. Real quick, I will just write up another one for you. Let's call this number 4. Let's say we're going to look up the tangent of, let's think of 150 degrees this time, right? This one is fairly straightforward because the angle is given in degrees. The angle is given between 0 and 360. So let's draw ourselves from the initial side, the terminal side, right here, 150 degrees. Let's drop our perpendicular down because here we have a reference angle, 180 minus 150 is equal to 30. Right, so this makes a 30, 60, 90 right triangle here in quadrant number 2. So the tangent of 150 is equal to the tangent of 30 degrees. right? So we can take this 150 and replace it with a 30 because 30 is the reference angle. But is this tangent function going to be positive or negative? Right, because this is in quadrant 2. The sine function is positive, which makes the tangent function negative. So if we look at 1 here, 2 at the hypotenuse, radical 3 opposite the 60-degree angle. Opposite is 1, adjacent is radical 3. That means the tangent of 30 is equal to 1 over radical 3, which is indeed negative. Thank you guys for watching, and I will speak to you soon. This tastes like burning.